Hello everyone and welcome to this lightning talk as part of the World Built Environment Forum series. My name is Andrew Knight and I lead all our work on data and technology within our thought leadership and analytics part of the Knowledge and Practice Directorate here at RICS. And today I wanted to spend 10 or 15 minutes just going through not all of the technical jargon that one is going to bump into in the world of increasing digitization across the built and natural environment, but a few key areas where I think it's worth understanding some of the terms and phraseology and the impact it's going to have on our profession right across the world. And really from that point of view, the first thing I'd like to look at is, a hugely busy area now, which is this whole topic of artificial intelligence. And I guess one of the challenges here is almost defining what we mean by artificial intelligence, which arguably is really the simulation of human intelligence by computer systems. And really what I think artificial intelligence can be summarized as doing is really having the ability to learn and to make decisions, interpret data based on experience, and to a large extent then reason based on those data that it's being used to actually be trained on and self-correct. And really, you can look at AI, I suppose, as being either kind of general AI in the kind of ways it can look at recruitment and general kind of horizontal applications like taking meeting notes that are really kind of profession and sector independent. And then you can have these really kind of strong, narrow AI where it looks specifically at some particular task. And that might well be something in the built environment, like looking at cost benchmarking data. It might be looking at image recognition to do with BIM models. So it could be something very, very specific where it's been trained to do a particularly narrow, specific task. I think what's also very important to understand is really how artificial intelligence systems are trained and are able to make these kind of human-like decisions, because training of AI is a critical part. One may think that artificial intelligence is all about code and algorithms and instructions, but classically many of the machine learning, which is a particular part of AI, is around teaching machines to understand through a large data set, to look at that data set and draw conclusions. And in fact, there are two main areas in which this sort of data training is used. One is called supervised learning, where effectively you tag images or sets of data, give that to the AI model, and therefore it uses that learning, it uses that tagged, that labeled data set to understand either perhaps from a construction perspective, the kind of costs that are being input, or it might be image recognition, but it's classically used to tag data. And that's what's called supervised learning. You then get the opposite of that, which is unsupervised learning, where you essentially give the model a whole data set once again, and you let the model effectively draw its own conclusions. And here you might use, as perhaps not a great example for the built environment, but you might give an unsupervised machine learning algorithm lots of pictures of fruit, for example, or vegetables, and it would begin to make its own decisions about how to categorize and interpret the data it's being given. And I think it's worth emphasizing that this unsupervised approach can be very powerful, because when you're relying on these artificial intelligence models to find patterns, to draw conclusions where a human being really can't predict, it's very useful to have this kind of unsupervised approach where you can use the data and allow the algorithm to range widely across that data set and come to its own conclusions about patterns, statistical correlations that perhaps a human being wouldn't have thought of and wouldn't really present itself to them. Now, it's been really impossible over the last few months really to ignore perhaps the latest revolution in AI, these so-called generative AI, large language models, services like ChatGPT, and we've seen really another explosion of the ability of AI, once again, trained on huge volumes of data to produce these human-like chatbots, this ability to both produce text based on instructions, but also to produce images, to create video, to create even music based on this huge data library that they have been trained on. So it's fair to say that AI has got a huge potential already to revolutionize the way we look at data, the way we're productive in terms of the tools. I know recently that Microsoft have been adding Copilot effectively to a number of their products, both programming tools to help programmers produce code much more quickly and have code written for them, and indeed to help people create emails, to create Excel spreadsheets using these kind of co-pilots approach. And in fact, today I posted a LinkedIn post, and the first thing I saw when I went in to create post was a prompt to say that AI would help me write the text. So it's becoming a very pervasive, under the bonnet kind of technology, artificial intelligence. Now, one thing that's also been very, very, I think, inextricably linked to AI over the last few years has been this whole concept of big data. And by big data, when we think particularly of perhaps some examples in the built environment, if we think of a smart building and the kind of volumes of data that are coming out of those kind of assets, we have a real challenge now in terms of the ability to interpret these large volumes of data, make decisions, particularly in real time, that can then be actioned. And perhaps if we think about how we define big data, there's a number of definitions that use the letter V, and I'm going to use a simple 4-letter definition here of 4 Vs, where we look at the volume of data, the sheer amount of data that's generated and collected. And once again, I'll use that example of a smart building with various sensors, where all that kind of information is coming through at a tremendous volume during the day. And also that data can be a huge variety. Some of it may be text, some of it may be images from the security system, some of it may be video or audio, and also you'll have sensor data coming through in terms of temperature, CO2 levels, various readings from machinery, plant and machinery within a building. So you've got that variety of data as well. And then you've got this velocity, this speed, this fact that actually if you're tracking the movement of people, the performance of your M&E equipment in an asset, you'll be getting that data coming through at incredible velocity, readings every minute in terms of people's movements around the building, people coming in and out of the building, sensors reporting perhaps every few minutes on temperature, et cetera, et cetera. So you've got that velocity. And then you've also got a real issue around veracity, as it's described, which is the fact that you've got a lot of unstructured data where actually you need to be able to understand how you can, in many ways, tidy that data up, clear it up, make sure that you turn unstructured data into structured data, which is easier to then analyze. And in this kind of context, it's very hard to separate almost the analytics of big data from the power of these artificial intelligence systems. So quite often one will be talking about big data and then immediately having to think, well, how can we use AI to actually interpret, make decisions? And a good prosaic example could be a relatively simple AI algorithm looking at the information coming out of a smart building to optimize your heating and ventilation, to make sure that actually it's being turned on, it's being monitored at the right level in terms of preventative maintenance, but also the actual controls are being analyzed constantly in a feedback loop to make sure that you're running that part of the building, which can often be a sizable percentage of the energy costs, in that most efficient way. So big data, machine learning, almost hard to untangle in many respects because they do literally in that sense relate together. Another term that I'm sure many of you will heard in many, many contexts is this concept of a digital twin, a digital replica of some kind of physical asset. And perhaps a good example to show the extreme and most powerful versions of digital twins are perhaps outside the built environment, where you think of a Formula One car where they can not only model the performance during race time, but they can use this digital twin to help them develop and optimize the performance of the car as they're developing, as they're building it. But if we bring ourselves back to the built environment, and once again, perhaps use this example of smart buildings, we can see how a digital twin can go beyond the original BIM model to give you a very strong visual indication of how an asset is performing in real time. And a purist would perhaps also define a digital twin as having not only that ability to record in a digital form both the geometry, the shape, the visualization of an asset, and also get a lot of information back from sensors and other kind of ways of gathering data. But critically in a digital twin, there needs to be really this feedback loop where this information is coming from the physical asset into this digital equivalent, and then that information is then being used in that feedback loop, that positive feedback loop, to then control the asset in some positive way. And once again, we come back again to big data and artificial intelligence being able to actually work with these digital twins to take these large, voluminous, high velocity, high variance data sets and then use that information in real time to control the building, to control the asset. And so as I say, digital twins have a real powerful role here to play in terms of optimizing buildings and being part of the solution to overall sustainability for real estate and the built environment by their ability to model, control, and optimize the performance of the building. One last area, I think that's a couple of last areas that worth briefly mentioning are also the the concept of the Internet of Things and cloud computing. And cloud computing, I think, particularly has a big role to play in terms of the kind of democratization of IT and digitization, because many firms do not want and cannot afford necessarily to maintain servers and software on site, on premises. And what cloud computing has done is allowed so many applications to be run in this so-called cloud, which is still physical data centers, but gives firms of every size the ability to run payroll, specific applications for the built environment, but do that on these major web services from firms like Amazon and Microsoft and Google Cloud, where you have this data centers replicated, spread across the world, and gives you the ability to run applications, store data on these distributed, well-protected, replicated data centers around the world. And I think it really is important for our profession, where so many firms are of this smaller size, that this cloud computing has given us what is called effectively software as a service, this ability to access software that's hosted on the cloud, the program runs on the cloud through a browser, the data is held securely, and it means you don't have to run servers and have that kind of overhead. And I guess one last area that we've kind of touched on before is once again the Internet of Things, where if we think of the smart buildings as another great example, we're looking at more and more, not only in the operational phase, but also during construction, the ability to have devices, sensors that are connected to the internet, whether that's a hard wire or whether that's done through wireless and other kinds of connectivity, but to have these sensors that allow you to monitor, particularly using a digital twin, and to really manage your assets in a much, much cleverer way. And some, as I say, in a construction cycle, that can be around building safety, about making sure that there are protected areas, understanding some of the health and safety risks when it comes to people with wearable technology, for example. And also in that operational phase, clearly the ability to have sensors that are connected to your network to report on all those issues of temperature and comfort, used by people, making sure you understand which parts of the building are being under and overutilized, for example, and those classic examples, once again, of controlling various devices in the building by using the ability to have that feedback, those sensors, that Internet of Things, to give you not only the control day to day, but also preventative maintenance, planned maintenance, understand how your equipment is working in that kind of asset. I guess one last caveat, I think, to the Internet of Things and so many of these areas of digitization for us in the built and natural environment is the cybersecurity, and really just being mindful that the more we have connectivity, the more we deal with data, the more we have a responsibility as a profession to make sure that we curate and protect data, both from a GDPR and a personal perspective, but also from a commercial perspective, that we make sure that data that's being recorded is used appropriately, and indeed that data is secure. So hopefully in this few minutes, I've given you a bit of an overview of perhaps some of the key trends, I think, in digitization that are affecting the built environment. AI in all its forms, that link to the big data sets that we're now dealing with, the power of digital twins to model and run assets, the power of cloud computing, and particularly the democratization that brings for smaller firms to be able to access all these powerful solutions. And then finally, the connectivity of the Internet of Things, despite the caveats of I've mentioned of cybersecurity. So thanks for listening. Been a pleasure to talk today.